Put your palm flat against a modern drywall interior wall during a hard cold snap, the kind where the temperature drops 15 degrees between midnight and dawn, and you can feel the room's temperature start to slide right along with it. Now put your palm against the inside of a real log wall on that same brutal night, the kind of wall a lot of old northern cabins and outbuildings still have. Holding them up, it is not warm exactly, but it is steady, holding its temperature almost stubbornly while the air on the other side of it is falling apart. That difference is not an accident, and it is not folklore. It is a piece of physics most modern houses gave up on for reasons that had nothing to do with comfort and almost nothing to do with the wall itself failing at its job. A log wall does not out-insulate a modern wall on paper. I want to say that plainly before I tell you why it still worked. A 6-inch softwood log wall has a clear wall R value of about 8. A standard stud wall packed with 3.5 inches of insulation lands around R14, on paper nearly double. If insulation value were the whole story, the log wall loses. But a solid log wall does something a stud wall full of fiberglass cannot do at all. And that is where this gets interesting. My name is Walter Northwood, and by the end of this, you will know exactly why a solid log wall holds a room's temperature through a cold snap, in a way a better insulated modern wall often cannot. What chinking and daubing actually are and why they mattered as much as the logs themselves, and the real documented reason this way of building nearly disappeared within a single generation, for reasons that had nothing to do with the technique failing. Here is the piece the R value number misses. It is called thermal mass, and it is the ability of a heavy, dense material to absorb heat and give it back slowly instead of all at once. A stud wall with fiberglass bats resists heat transfer, but it does not store meaningful heat itself. A solid log wall does both. Through the day, it slowly absorbs warmth. As the temperature outside drops hard and fast, that stored heat radiates back into the room instead of the wall simply resisting the cold, the way an insulated cavity does. Building codes now formally recognize this. The International Energy Conservation Code includes what is called a mass wall provision, specifically because solid materials like logs, concrete, and masonry perform differently than the R value number alone suggests, especially in climates with a big swing between day and night temperatures, which describes a northern winter about as well as anything does. A 10-inch log wall reaches roughly R14 on its own, competitive with a standard stud wall, and then adds the mass effect on top of that. Here is the part that surprises people once they actually understand it. The thicker the log, the less the raw insulation number matters, and the more the mass effect takes over, which is the exact opposite of how most people assume insulation works. A thin log wall behaves more like ordinary wood. A thick one starts behaving like a flywheel for heat, soaking up a full day's worth of sun and wood stove warmth, and metering it back out slowly enough that a single brutal night can pass without the room ever fully catching up to the cold outside. None of this worked without the second half of the wall, though, and that half almost never gets talked about. Logs are round or hewn flat, never perfectly uniform, which means gaps form between them no matter how carefully they are stacked. Those gaps got filled with a two-part system. First, a rigid filler, split wood, stone, sometimes brick, packed into the gap to take up most of the space. Then, over that, a softer packing material, moss, clay, dried mud, sometimes lime mixed with sand, pressed in to seal the remaining gap and finished with a smoothed outer layer. The rigid filler was called chinking. The finished layer was called daubing, though most people use the word chinking for the whole job. The materials changed by region: moss in the thickly forested north, clay and mud further south and west, whatever the land actually gave a family to work with. Here is the honest problem with it, because I am not going to pretend this was a perfect system. Wood moves. Logs expand and contract with humidity and temperature, swelling in summer and shrinking in a hard winter, and the chinking material does not move the same way the wood does. Over years, cracks open at the seams between log and chinking, and that is exactly where the draft gets back in. A log wall was never a one-time job. It needed regular inspection and regular repair, a family checking the seams every year or two the same way they'd check a roof, repacking anywhere the chinking had pulled away. Skip that maintenance for long enough and the whole thermal mass advantage stops mattering, because the cold just walks in through the gaps instead of coming through the log itself. Here is something worth knowing if you actually own one of these structures. The old lime, clay, and mud chinking was never the end of the story. The people who still build and restore log homes today mostly move to a synthetic version instead, a flexible, rubber-like sealant sold under names like Permachink and Log Jam, colored and textured to look exactly like traditional mortar chinking from a few feet away. The reason is exactly the weakness I just described. Where old-style mortar chinking is rigid and cracks as the logs move, the synthetic version stretches up to 2.5 times its own width and keeps its seal as the wood expands, contracts, and settles over the decades, with a working life of 20 to 30 years before it needs redoing. The technique did not vanish. It adapted quietly inside a small industry most people outside of log construction have never heard of. Corner construction mattered just as much as the wall itself. Logs were joined at the corners using notches cut to lock them together without a single nail, the saddle notch and the dovetail notch being the two you'll see most often on an old northern cabin still standing today. A dovetail notch, cut at an angle on both the top and bottom of each log end, actually sheds water away from the joint and tightens under the weight of the logs above it as the structure settles, which is part of why some of these corners have survived over a century of freeze and thaw with barely any chinking work at all. A saddle notch, the rounder, simpler cut you'll see on plenty of quickly built early cabins, went up faster but did not lock nearly as tight, which is exactly the kind of trade-off that shows up again and again in how these structures were actually built. Speed against tightness, available skill against available time, and every builder made that call a little differently depending on whether the cabin needed to go up before the first snow or was meant to stand for a lifetime. Now, why did this whole way of building nearly vanish inside of about 2 generations? It was not that anyone decided log walls did not work. It was industrial. In the early 1800s, a water-powered sawmill could cut somewhere around 1,500 board feet of lumber in a day. By the 1850s, steam-powered mills were routinely cutting close to 30,000 feet a day, and by the 1890s, some mills were pushing near 100,000. Machine-cut, standardized dimensional lumber became cheap and available almost everywhere a railroad could reach. At the same time, steam-powered nail-making machines were turning out tens of thousands of machine-made nails a day, when nails used to be hand-forged one at a time. Put cheap standardized lumber together with cheap machine-made nails, and you get balloon framing, a way of building a house's walls out of thin studs and nails that required far less timber, far less skilled labor, and went up in a fraction of the time a log structure took to notch and stack and chink by hand. Unskilled labor could frame a house. Log construction genuinely could not be rushed the same way. By the early 20th century, balloon framing was simply the faster, cheaper way to put a roof over a family's head, and thermal mass was not part of anyone's calculation when speed and cost were what mattered most. A log wall might take a skilled team weeks to notch, stack, and chink properly. A framed wall of the same size could go up in days with a crew that had never framed a house before that week. When a family or a town was choosing between the two, the choice was rarely close. I want to be honest about where this does and does not apply to you. Very few people are building a new log home from scratch, and I am not telling you to. But if you own an old log structure, a cabin, a barn, an outbuilding, the lesson is direct. That thermal mass advantage only exists if the chinking is doing its job. Walk the seams every year or two. Look for cracks where the fill has pulled away from the wood, especially on the side that takes the worst of the winter wind, and repack it before the next hard freeze, not after you've already felt the draft. And if you're building anything new with an eye toward genuine cold weather performance, whether that's a woodshed, a workshop, or an addition, the underlying principle still holds. Mass stores heat. Fiberglass alone does not. The two work best paired together, not as a choice between one or the other. A concrete or masonry knee wall behind a wood stove, a stone hearth pad that runs floor to ceiling instead of stopping at the mantel, even a simple brick interior wall catching the afternoon sun through a south-facing window, all of it is the same principle those log walls were doing for free. just in a smaller, more targeted dose than an entire house built out of it. Old-timers did not call it thermal mass, and most of them could not have told you the R-value of anything. They just knew a thick wall held a room steady when the sky turned mean, and a thin one did not, and they built accordingly with whatever their land actually gave them to work with. If you've got an old log structure on your property, tell me in the comments what shape the chinking is in, and how old the building actually is. Subscribe if you want to keep seeing what these old houses actually got right, one piece of the wall at a time. And if you're the kind of person who wants to understand a house from the ground up instead of taking a contractor's word for it, stay close, because the walls were only one piece of what these old places got right.